Welcome to Evo AI, where we navigate the intriguing evolution of artificial intelligence. I'm your host, Bogdan Yanku, and in this series, we'll explore how artificial intelligence is transforming the way we work, innovate, and grow. From small startups to corporate giants, we'll unravel the mysteries of AI, uncovering insights, strategies, and the real-world impact on our everyday lives. Whether you're in sales, finance, marketing, human resources, or just curious about artificial intelligence, Evo AI has something for you. Hello, friends, and welcome to another episode of AI Unlocked. Today, we will cover a topic that is really close to my heart. This is how I got acquainted with large language models. That's right, the first thing I learned on my AI journey was about encoder-decoder mechanisms, and that's what we're going to cover today. But before we begin, just a quick reminder that if you like our podcast and want to know more, please follow us on Spotify, Apple, Google Play, iHeartRadio, Amazon Music, and Radio Public. So let's start. In the dynamic landscape of machine learning and AI, the encoder-decoder mechanisms have emerged as a pivotal concept. Their inception marked a significant shift in how we approached complex problems, particularly in the domain of neural machine translation, or NMT. Neural machine translation, or NMT, is a paradigm shift in the domain of machine translation. Traditional machine translation models relied on complex rule-based systems where linguistic experts would manually define rules for translating text from one language to another. While effective to some extent, these models had their limitations, struggling with idiomatic or colloquial expressions and often producing translations that, while technically correct, lacked the natural flow of human language. NMT, on the other hand, leverages the power of neural networks to translate text. Instead of relying on predefined rules, NMT models are trained on vast datasets containing pairs of sequences in both the source and target languages. Over time, the model learns the intricate nuances, idioms, and structures of both languages. When given a new sentence in the source language, the NMT model can produce a translation in the target language that is not only accurate, but also sounds natural. The beauty of NMT lies in its ability to consider the entire input sequence, capturing the context and semantics, which is crucial for producing high-quality translations. The holistic approach is where the encoder-decoder mechanism shines. The encoder processes the input sentence, capturing its essence, while the decoder produces the translation, ensuring it retains the original meaning and context. In essence, NMT has transformed the field of machine translation, offering a more efficient, accurate, and context-aware solution. Its influence is evident in the many of the translation tools and services we use today, making cross-cultural communication smoother and more accessible than ever before. Historically, machine learning models were designed to handle specific tasks, often limited by computational constraints and data availability. However, as technology advances and datasets grew, there was a pressing need for models that could handle sequential data, process it, and produce meaningful outputs. Enter now the encoder-decoder paradigm. The encoder-decoder model operates on a simple yet very effective principle. The encoder processes the input data, creating a condensed representation of it. Think of this as a business leader summarizing their company's vision into a concise strategy. This representation, often termed the context, holds the essence of the input. Following this, the decoder takes over, expanding the context into the desired output. In the realm of machine translation, for instance, the encoder might process an English sentence, and the decoder would produce its French counterpart. But it's not just about translation. The applications of encoder-decoder mechanisms are vast, spanning various sectors and industries. From voice recognition systems to video captioning, the influence of this model is undeniable. As we progress with our podcast today, we'll delve deeper into the nuances of the encoder-decoder model, its evolution challenges, and the revolutionary attention mechanism that enhanced its capabilities. We'll also touch upon its real-world applications, recent developments, and what the future holds for this fascinating mechanism. So whether you're well-versed in machine learning or new to the subject, this journey promises a comprehensive understanding of one of the most influential models in the world today. So let's start. We spoke briefly about neural machine translation, or NMTs, which we said that neural machine translation represent a significant shift in the approach to machine translation. To truly grasp its importance, we need to understand its evolution and the problems it addresses. Historically, machine translation was dominated by rule-based and statistical methods. In rule-based systems, linguistic experts manually defined a set of rules to translate text from a source language to a target language. While this method had its merits, it was inherently limited. Each new linguistic exception or idiom required a new rule, making the system cumbersome and less capable to the fluid nature of language. Statistical machine translation (SMT) followed, which used statistical models to predict the likelihood of a sentence in the target language given a sentence in the source language. These models were trained on large bilingual datasets, and while they were more flexible than rule-based systems, they still struggled with long sentences and maintaining context over longer sequences. This is where NMT comes into play. Unlike its predecessors, NMT uses deep neural networks to translate entire sentences rather than breaking them down into smaller chunks. The process begins with the encoder, which converts input sentence into fixed-size vector representation. This vector captures the semantic essence of the input. The decoder then takes this representation and generates the translation, ensuring that the output maintains the context and meaning of the original sentence. One of the primary advantages of NMT is its ability to manage and remember context over longer sequences, leading to more accurate translations. Moreover, since it's based on neural networks, the system can be continuously trained and improved upon with more data, making it adaptable and scalable. However, NMT is not without challenges. The quality of translation heavily depends on the amount and quality of training data available. Additionally, while NMT models excel in many scenarios, they can sometimes produce translations that are grammatically correct but contextually odd. Researchers and engineers are continually working on refining and improving these models to address such issues. In a broader perspective, NMT has significantly impacted global communication. Businesses, researchers, and everyday users benefit from its capabilities, making interactions across different languages smoother and more accurate. As we progress, we'll delve deeper and deeper into the mechanisms that power NMT and explore the innovations that are shaping the future. The encoder-decoder architecture, while conceptually straightforward, is an amazing blend of intricate design and functionality. To truly grasp its inner workings, let's dissect the process using a simple sentence such as "Hello world." When this sentence is fed into the encoder, each word and even each character plays a pivotal role. The model doesn't just see words, it sees a sequence of tokens, which can represent characters, words, or even subwords, depending on the granularity of the model. Each token is then represented as a high-dimensional vector using embeddings, which capture the semantic meaning of the token. The encoder processes these embeddings through multiple layers, often composed of recurrent neural networks, or RNNs, or long short-term memory networks, or LSTMs. These layers allow the model to understand the context of each token based on its position in the sequence and its relationship with other tokens. For instance, in our sentence, "Hello world," the model recognizes hello as a greeting and world as an entity being greeted. As the sentence progresses through the encoder's layers, the model continuously refines its understanding. By the time it reaches the final layer, it has condensed the entire sentence into a dense context vector. This vector, while compact, encapsulates the essence and structure of the input sentence. Now the decoder takes the stage. Starting from the context vector, it begins the task of generating the output sequence. If we were translating our sentence into another language, the decoder would use the context vector to produce a translation that retains the greeting context of "Hello world." The decoder, similar to the encoder, also has multiple layers. As it generates each token of the output sequence, it references the context vector to ensure the output remains contextually relevant to the input. The magic here is the iterative nature of the process. The decoder doesn't just use the context vector, it also considers the tokens it has already generated to influence the generation of subsequent tokens, ensuring coherence in the output. However, with longer sequences, the traditional encoder-decoder model faced challenges. This is where the attention mechanism comes into play. Instead of relying solely on the context vector, the attention mechanism allows the decoder to focus on different parts of the input sequence dynamically, giving weight to specific tokens that are more relevant at each step of the decoding process. It's like highlighting crucial points in a report, ensuring that no vital detail is overlooked. In essence, the encoder-decoder's model's strength lies in its layered architecture, its ability to understand context through token relationships, and its iterative decoding process, enhanced by the power of attention. It's a blend of precision, context awareness, and adaptability, making it a cornerstone in sequence to sequence tasks. The attention mechanism, which is a relatively recent innovation in the neural network landscape, has quickly become indispensable, especially for sequence to sequence tasks. But what is it about that mechanism that has caused such a transformative impact? To understand attention, let's first clarify two fundamental concepts: tokens and weights. In the realm of neural networks, a token typically refers to an individual piece of data, be it a word, character, or subword that the model processes. For instance, in our hello world example, each word can be considered a token. Weights, on the other hand, are numerical values that determine the importance or influence of these tokens. In the context of attention, weights dictate how much focus or attention a particular token from the input sequence should receive when generating the output. As we delve deeper into the intricacies of neural networks, it's crucial to differentiate between the number of tokens a model can handle and its overall size. Tokens, as we've discussed, represent individual pieces of data, like words or characters. The number of tokens a model can process in a single pass determines its capacity to handle long sequences. On the other hand, the model size refers to the number of parameters it contains. These parameters, which include weights and biases, determine the model's capacity to learn and represent complex functions. A model with more parameters is generally capable of capturing more intricate relationships in the data, but also demands more computational resources and is prone to overfitting if not trained properly. Interestingly, while there's a relationship between the two, as models grow in size, they often can handle more tokens, they are not directly proportional. It's possible to have a large model in terms of parameters that's optimized for shorter sequences. Conversely, certain architectures might handle longer sequences with more tokens without a massive increase in overall model size. Understanding this distinction is pivotal, especially when optimizing models for specific tasks or computational constraints. Now, imagine reading a detailed business report. While every section is crucial, certain sentences or words naturally stand out based on your current context or objective. The attention mechanism mirrors this behavior in neural networks. When the decoder, in an encoder-decoder model, crafts an output sequence, it doesn't uniformly consider every part of the input. Instead, it attends to specific tokens that are most relevant for the current step of the output. This dynamic focusing capability allows the model to capture intricate relationships and long range dependencies in the data that might otherwise go unnoticed. Returning to our hello world example, when translating this into another language, the token hello, representing a greeting, might heavily influence the formulation of the greeting in the target language. The attention mechanism, recognizing this significance, assigns a higher weight to hello, ensuring the translation encapsulates the essence of a greeting. Technically, the attention mechanism calculates a set of weights for each token in the input sequence. These weights, recalculated at each decoding step, determine the attention each token should receive. This adaptability, recalibrating focus based on the evolving context of the output, is a hallmark of the mechanism. The implications of these dynamic attention allocations are profound. It not only elevates the quality of machine translations, but also boosts performance in domains like speech recognition, image captioning, and even areas beyond sequence modeling. However, the attention mechanism, despite its prowess, has challenges. As models burgeon in size and intricacy, the computational demands of attention calculations intensify. The research community is fervently exploring optimization and alternative strategies to enhance efficiency without diluting effectiveness. In summary, the attention mechanism has redefined how neural networks interpret and generate sequences. By enabling models to concentrate on pivotal data aspects, it introduces a depth of nuance and context awareness previously hard to attain. The landscape of neural networks and machine learning is continuously changing, with innovations emerging at a rapid pace. Since the last 2 years, since 2021, the encoder-decoder models have witnessed a series of advancements that have both refined their capabilities and broadened their applications. A significant stride in the domain is the adoption of transfer learning. At its core, transfer learning involves taking a pre trained model, which is a model trained on a large data set, and fine tuning it for a specific task. This approach capitalizes on the knowledge the model has already acquired, allowing for a quicker training and often better performance, especially when the available data for the specific task is limited. While our focus isn't on transformers today, it's pivotal to recognize their influence. These architectures introduce self attention mechanisms, enable models to weigh different parts of an input sequence based on their relevance, irrespective of their positional distance. This enhancement has been previously beneficial for tasks like document summarizing and question answering. Few shot and zero shot learning. These techniques are revolutionizing the way models are trained. Few shot learning enables models to make predictions based on a minimal set of examples, while zero shot learning empowers them to predict classes they've never encountered during training. This is groundbreaking, especially for tasks like translation, where certain language pairs might lack extensive datasets. Multimodal learning. At its essence, multimodal learning refers to models designed to process and relate information from multiple types of data, such as text and images. This capability has paved the way for applications like generating textual descriptions for visuals or translating spoken content into sign language. Let's talk briefly about model optimization techniques. One of those models is model pruning. This involves trimming unnecessary parts of a neural network, reducing its size without significantly affecting its performance. It's akin to streamlining a complex business process, retaining only the essential steps. Quantization. This technique reduces the numerical precision of the model's weights, making the model smaller and faster with a minimal trade off in accuracy. Knowledge distillation. Here, a smaller model, let's call it the student, is trained to replicate the behavior of a larger model, more complex one. Let's call that the teacher. The student learns from the teacher's output, resulting in a compact model that retains much of the teacher's prowess. Lastly, the drive towards enhanced model interpretability is gaining momentum. As these models undertake increasingly intricate decisions, the ability to decipher their reasoning becomes crucial. Efforts are underway to develop methods that visualize and interpret the decisions of encoder-decoder models, fostering transparency and ease of debugging. Let's look now at some practical applications of encoder-decoder models. The theoretical underpinnings of encoder-decoder models, while fascinating, truly come to life when we see them in action. These models have been instrumental in a myriad of applications, transforming industries and enhancing user experience across the board. Perhaps the most well known application, encoder-decoder models have revolutionized the field of machine translation. Gone are the days of rudimentary and often inaccurate translations. Modern systems powered by these models can translate entire documents while preserving nuances, idioms, and cultural context, bridging communication gaps globally. Google Translate, for example, utilizes the T5 model, a transformer-based encoder-decoder architecture to translate text between languages, making communication seamless across linguistic barriers. Speech recognition. Transcribing spoken language into text is no small feat, given the variations in accents, intonations, and speech patterns. Encoder-decoder models excel here, converting audio signals, which are encoded, into textual data, which is decoded with remarkable accuracy. Apple's Siri and Google's voice search employ advanced encoder-decoder models to transcribe and understand user voice commands, facilitating hands-free interactions. Image captioning. Moving beyond text, these models have ventured into the realm of visual data. Image captioning involves generating descriptive text for a given image. The model encodes the visual information and then decodes it into a coherent caption, enabling a synthesis of visual and textual understanding. Google's Cloud Vision API offers image captioning capabilities where encoder-decoder models generate descriptive text for uploaded images, aiding in content categorization and search. Video summarization. With the explosion of video content online, there's a growing need for concise summaries. Encoder-decoder architectures can process video frames, encode the salient features, and then decode them into succinct summaries, aiding content discovery and accessibility. Platforms like YouTube use encoder-decoder models to generate video captioning and potentially summarize content, enhancing accessibility for diverse audiences. Chatbots and virtual assistants. The conversation agents we interact with daily, be it Siri, Alexa, or customer support chatbots, leverage encoder-decoder models. They encode user queries and decode them into appropriate responses, facilitating natural and dynamic interactions. Facebook's M2M100 is a massive multilingual machine translation model that can translate between 100 different languages, powering chatbots and virtual assistants to communicate in multiple languages. Medical diagnostics. In the healthcare sector, these models are making waves. They can analyze medical images, encode the features, and decode them back into diagnostic reports, assisting medical professionals in making informed decisions. Companies like Path AI use encoder-decoder models to analyze medical images, generating diagnostic reports that assist doctors in identifying diseases and planning treatments. Music generation. On a more artistic note, encoder-decoder models have ventured into music generation. They can encode existing musical pieces and decode or generate new compositions, pushing the boundaries of machine creativity. OpenAI's Jukebox and Stable Diffusion Stable Audio are deep learning models that generate compositions in various styles of music. They encode musical pieces and decode or generate new compositions. Predictive text and autocomplete. A daily utility for many, predictive text systems encode the words you type and decode or predict the next likely word or phrase, enhancing typing speed and efficiency. SwiftKey, a popular keyboard app, uses encoder-decoder models to predict the next word a user is likely to type, enhancing the typing experience. In essence, the applications of encoder-decoder models are vast and varied. From daily utilities to specialized professional tools, they've seamlessly integrated into our lives, enhancing efficiency, accuracy, and even creativity. As advancements continue, we can only anticipate an even broader spectrum of applications, further testament to the versatility and power of the encoder-decoder mechanism. The world of deep learning is vast, and while transformers have been a significant breakthrough, there are several other architectures that have made notable contributions to the field. The first one, the decoder-only models. As previously discussed, decoder-only models have a unique architecture that focuses solely on the decoding aspect. They process a continuous stream of data, generating outputs without the traditional encoding phase. Their efficiency and flexibility make them suitable for specific applications, especially where real-time data processing is paramount. Recurrent neural networks, or RNNs. Before transformers took center stage, RNNs were the go-to model for sequence-to-sequence tasks. They process sequences step by step, maintaining an internal state from one step to the next. While they've been somewhat overshadowed by the efficiency of transformers, RNNs, especially their advanced variants like LSTM, long short term memory, and GRU, gated recurrent units, still find applications in tasks where sequence continuity and memory are crucial. Convolutional neural networks, or CNNs. Primarily known for their prowess in image processing, CNNs have also been adapted for sequence to sequence tasks. By employing a hierarchy of convolutional layers, they can capture local and global patterns in data. In the realm of natural language processing, 1D CNNs have been used for tasks like sentiment analysis and text classification. Sequence to sequence models with attention. Before the transformer's self attention mechanism became popular, traditional sequence to sequence models were augmented with attention mechanisms to improve their performance, especially in tasks like machine translation. The attention mechanism allowed these models to focus on specific parts of the input sequence when generating outputs, enhancing accuracy and context preservation. Autoencoders. Used primarily for unsupervised learning tasks like dimensionality reduction and anomaly detection, autoencoders consist of an encoder that compresses the input and a decoder that reconstructs it. Variational autoencoders, or VAEs, and denoising autoencoders are popular variants with specific applications in generative tasks and noise reduction, respectively. Advantages beyond transformers. First one, diversity. Different architectures offer diverse ways of processing data, each with its strengths and weaknesses. This diversity allows for tailored solutions based on the task at hand. Another one is legacy and adaptability. Many older architectures like RNNs have a rich legacy of research and applications. Their adaptability, especially when augmented with newer mechanisms like attention, ensures they remain relevant in specific scenarios. Another one is specialization. While transformers are generalists excelling in a wide range of tasks, some architectures are specialists, optimized for specific tasks or data types. In conclusion, while transformers have set new benchmarks in numerous applications, the broader landscape of neural network architectures is rich and varied. Each model brings unique capabilities to the table, and understanding their nuances allow for more informed choices in real-world applications. Let's now explain the notions of training and fine-tuning. What are those? Deep learning models, like the complex machinery they are, require calibration and refinement to function optimally. This calibration process occurs in two main stages: one, training, and two, fine tuning. Let's start with training, laying the foundation of deep learning models. It starts with data ingestion. The model is exposed to a vast dataset, often containing millions of data points. This dataset provides the raw material upon which the model builds its understanding. Then it continues with weight adjustment. As the model processes the data, it continuously adjusts its internal parameters known as weights. These adjustments are made based on the error between the model's predictions and the actual outcomes. The goal here is to minimize this error. Then, epochs and iterations. Training isn't a one-time process. The model goes through the dataset multiple times, in epochs, refining its weights with each pass. Each epoch consists of several iterations where batches of data are processed. Finally, overfitting and regularization. A crucial aspect of training is ensuring the model doesn't overfit, meaning it doesn't become too tailored to the training data, losing its ability to generalize. Techniques like dropout and L2 regularization are employed to prevent overfitting. Now, let's look at what fine tuning is. It's model specialization. It starts with domain specific refinement. Post the foundational training, models are often fine tuned on specific datasets. This dataset is narrower in scope, allowing the model to specialize. It can also contain transfer learning, One of the powerful aspects of fine-tuning is transfer learning. Models trained on one task can be fine-tuned for another, leveraging the knowledge gained during initial training. This is especially beneficial when the new task has limited data. It can also include hyperparameter tuning. Along with weight adjustments, fine tuning can also involve tweaking hyperparameters like learning rates, batch sizes, and more to optimize performance. Let's look at some real world analogies. Well, training is like general education. Just as a student undergoes general education to gain foundational knowledge across subjects, models undergo training to understand the broad patterns in data. Fine tuning is akin to majoring. Students then choose a major to specialize in a specific field. Particularly, models are fine tuned to excel in specific tasks. Consider the realm of image recognition. A model might initially be trained on the ImageNet dataset, learning to recognize a plethora of objects. However, if a museum wants to use this model to identify and categorize specific art styles, the model would be fine tuned on a curated datasets of art pieces, allowing it to distinguish between, say, Baroque and Renaissance art with precision. In essence, training sets the stage, laying the foundational knowledge, while fine tuning refines this knowledge, ensuring the model is tailored and optimized for specific tasks. Together, they ensure that deep learning models are both versatile and precise. Let's now talk about inference in encoder-decoder mechanisms. In the realm of deep learning, once the rigorous phases of training and fine tuning are completed, the model is set to perform its primary function, making predictions on new data. This phase is termed as inference. Let's understand what inference is. During inference, the model utilizes the weights and biases it has learned during training to make predictions. It doesn't alter these weights. Instead, it applies them to new data. Inference is typically faster than training since the model isn't adjusting its weights. It can process data more swiftly. Optimizations like model quantization can further boost inference speed. Where inference applies in encoder-decoder models? Well, in the encoding phase, for example. The encoder takes the input data and processes it to generate a context vector. This vector encapsulates the essence of the input data, serving as a compact representation. Also, in the decoding phase, the decoder takes this context vector and generates the output. It deciphers the information in the context vector, producing a result that aligns with the model's training. Some practical applications of inference. One, machine translation. As highlighted before, a model trained for English to French translation will, during inference, take an English sentence and produce its French counterpart. The encoder captures the semantics of the English sentence into a context vector, and the decoder translates this into French. In terms of speech recognition, in applications like speech to text, the encoder processes audio data, creating a context vector that captures the spoken content. The decoder then translates this into corresponding text. What about image captioning? Well, for tasks where an image needs a descriptive caption, the encoder processes the image and the decoder generates a fitting description. Let's talk about some challenges and considerations. Let's look at handling ambiguity. Especially in tasks like translation, there can be multiple valid outputs. The model must be adept at choosing the most contextually appropriate one. Also, maintaining context for long sequences, ensuring that the decoder maintains the context from the encoder can be challenging sometimes. This is where mechanisms like attention play a pivotal role, helping the model focus on relevant parts of the input. In conclusion, inference is where the model's capabilities are truly put to the test. It's the phase where all the learnings, adjustments, and refinements bear fruit, allowing the model to perform its intended tasks on real world data. The introduction of attention mechanisms in deep learning models have been nothing short of transformative. It has redefined the way encoder-decoder models process and understand data, especially in sequence-to-sequence tasks. The essence of attention mechanisms. 1. Dynamic focusing. At its core, Attention allows the model to dynamically focus on different parts of the input data when generating the output. Instead of treating all input parts equally, it assigns varying degrees of importance based on context. Number two, weighted summation. The attention mechanism computes weights for each part of the input. These weights are then used to produce a weighted sum of the input data, which the decoder uses to generate the output. Let's talk a little bit about training with attention. Number one is learning to attend. During training, the model learns to assign these attention weights effectively. It adjusts these weights to minimize the difference between its predictions and the actual target outputs. Then it's capturing relationships. With attention, the model can capture long range dependencies and intricate relationships in the data, which might be challenging for models without attention. Teacher forcing. That's something that boosts training. 1. Guided learning. Teacher forcing is like guiding a student by providing the correct answers during practice. Instead of using its predictions, the model is fed the actual target output for subsequent steps. Then we have the accelerated convergence. This technique often speeds up the training process. By providing the model with the correct answers, it doesn't stray too far off the path, leading to faster and often more stable convergence. The power of attention in practice. Let's talk about that. One, well, handling long sequences. In tasks like machine translation, where sentences can be lengthy, attention ensures that the model doesn't lose context, even for distant words or phrases. Then, improved efficiency. Models trained with attention often achieve comparable or even superior performance in reduced training time. The focused nature of attention means the model spends less time on irrelevant data and more on what truly matters. What about some real world analogies? It's like reading with a highlighter. Well, think of attention really as reading a book with a highlighter. Instead of giving equal importance to every word, you highlight or attend to, if you want, specific phrases or sentences that capture the essence or are crucial to understanding the context. In conclusion, attention mechanisms have ushered in a new era in deep learning, especially in the realm of encoder-decoder models. By allowing models to focus and attend to specific parts of the data, they capture context and relationships with unparalleled precision. When combined with techniques like teacher forcing, the training process becomes more efficient, leading to models that are both accurate and robust. As we draw our exploration of encoder-decoder mechanisms to a close, it's essential to cast our look forward, envisioning the trajectory of these powerful models in the ever-evolving landscape of deep learning. So let's talk about the future of encoder-decoder mechanisms. Beyond text and speech, while encoder-decoder models have made significant strides in areas like machine translation and speech recognition, the future promises expansion in newer domains. We might see these models playing pivotal roles in fields like bioinformatics and decoding complex biological data. Enhanced efficiency for these models. As computational power grows and algorithms become more refined, we can expect even more efficient encoder-decoder models. These models will be capable of processing vast amounts of data in real time, opening doors to applications we've yet to imagine. In terms of synergy with other technologies, let's talk about that. One, augmented reality, AR, and virtual reality, VR. Imagine an AR system that uses encoder-decoder models to translate signboards in real time as you walk through a foreign city, or a VR educational platform that provides instant translations of complex scientific terms. What about IoT and smart devices? Well, as our homes and cities become smarter in the future, encoder-decoder models will play a role in processing and translating vast streams of data from various sensors, ensuring seamless communication between devices. Let's look now at some challenges and considerations too. One, ethical implications. As with all powerful technologies, there will be ethical considerations. Ensuring that these models are used responsibly, without biases, and respecting privacy will be paramount. In terms of continuous learning, well, the dynamic nature of data means that models will need to adapt continuously. Future encoder-decoder mechanisms might incorporate more robust lifelong learning capabilities, allowing them to evolve with the new data they process. There's a world of possibilities out there for the encoder-decoder mechanisms. One is interdisciplinary collaboration, which is the most important one because the potential of encoder-decoder models isn't just limited to tech. Collaborations between technologists, biologists, linguists, and even artists can lead to groundbreaking applications enriching human experiences. Well, I hope that this journey through the intricacies of encoder-decoder mechanisms and attention models has been informative. But let's all remember, this is just the tip of the iceberg. The field of deep learning is vast, dynamic, and ever-evolving. As we stand on the cusp of numerous technological breakthroughs, the onus is on us to dive deeper, explore further, and harness these tools responsibly to shape a better future. Thank you for joining me again on another episode of AI Unlocked. If you like this episode and want to know more, please remember to subscribe on our website at evoai.ai and follow our podcast on Spotify, Apple, Amazon Music, Google Play, iHeartRadio, and Radio Public. Until next time. Well, that's a wrap of today's episode of Evo AI. We've delved into the fascinating world of artificial intelligence, unlocking insights that are changing the face of business today and tomorrow. But the exploration doesn't end here. There's always more to discover. Well, I'm Bogdan Iancu, and this has been Evo AI. Together, we're part of something bigger, much bigger, a movement towards understanding, innovation, and growth. Well, if you enjoyed our journey today, don't forget to subscribe and please join us again as we continue to explore the future of AI in business. Until next time, keep evolving.